Hi, welcome to Social Research Insights. My name is Kamakshaya. I'm going to discuss with you. Today I'm going to explain you how to do binary logistic regression by using PSPP installed in Ubuntu 16.04. And if you would like to know something about binary logistic regression, you just have to go to the browser and search for binary logistic regression. You'll have a wonderful Wikipedia page, and I don't think you might require anything more than Wikipedia as far as statistics and mathematics are concerned. But for other advanced calculations, you might require a refereed textbook or maybe a scholarly papers. But for basic statistics, you can just confine to the Wikipedia, and you have a wonderfully written description for binary logistic regression given in the Wikipedia. And here you can observe one particular expression for predicting the probability of some certain response. Usually in binary logistic regression, we'll follow an expression known as 1 divided by 1 plus e to the power of minus beta 1 x minus beta naught. So let me give you a detailed note on this. Given a logistic regression case like this, just as let me take y as usual is equal to beta naught. Usually this is a simple logistic regression notation that we follow while performing the statistical analysis, especially related to simple linear regression. Beta 1 multiplied by x plus some error. Okay, anyway, this particular part of the expression is not important right now for us. Given some regression expression in this way, where y is the dependent variable, and in this case a dependent variable must be a dichotomous variable because we are performing the binary logistic regression. So a dichotomous variable might be having only two responses, just like yes or no. You can have a response like yes or no, or you can have a response like gender, like male and female. You can also have a response like satisfied, dissatisfied, or something like that. But see that your response always must be dichotomous in nature, and x can be some continuous variable. So it doesn't matter what sort of, you can have some randomly generated data in x, and but y given some dichotomous data, then we might go for binary logistic regression in order to predict the response variable described by the random variable, which we assume here as the independent variable. So given this scenario or situation, we can just simply fit some binary logistic regression where the probability associated with that particular response, like y is equal to either 0 or 1, given x, is going to be the ratio of 1 to that of 1 plus e to the power of let's say minus of beta 1 x minus beta naught. So this is what is actually the expression that we need to use in order to predict the response of the dependent variable. So we need not do all these things in manually, because we have a wonderful software called PSPP. Especially if you are open source expert like Linuxian, then probably you can just install PSPP by going to the software center and there and start doing the analysis. You have a wonderful menu called Analyze, where you can do some descriptive statistics like frequency tables, descriptive analysis, and cross tabulation. And you can also make some mean comparisons by performing one sample t-test, or maybe independent sample t-test, or paid sample t-test, one way, blah blah blah. And you have a bivariate correlation analysis, where this particular technique will return the Calc Pearson coefficient R along with the significance values, and cluster analysis, factor analysis, reliability analysis, and finally regression. So we are going to make use of this particular submenu, regression, to perform the binary logistic regression. And to do that, I need to have some data. And in this example, I'm just going to make use of some simulated data. I'm going to simulate the data set for this particular statistical technique. For that, I can create a syntax editor. I can write some syntax in the syntax editor, through which we can create some bivariate data set which we require in order to perform this binary logistic regression. The code is very simple. Of course, you need not do all these things. You can just simply go to the Calc, where you can, this is only for the testing purpose. I'm not talking about, actually you are not going to simulate the data. Most of the time we will be having some data which we get from the field, or maybe from some secondary data sources. In case if your requirement is to test the software, like sometimes when we, so you usually will not be simulating datasets, but for study purposes there is nothing wrong if you can simulate the data. As I said, your y variable is going to be the dichotomous. You can just take 0, 1, 0, 1, something like this, and your x can be some random data, something like, you can just go for I think you can make use of some internally available functions like ran, maybe multiplied with 100, something like this. And here you can make use of some rand between. So I just wanted to show you what sort of data you should, the type of the data that you need to deal with when you are performing the binary logistic regression. So after doing this, you can also import this data by going to the PSPP. Just have to go to the file and there open the data set. I think this Calc, which is a spreadsheet that need to be converted into CSV file, and then after that you should go to the file and import the data, where you have to just choose the CSV file here, the type of the file, and after that, and numeric I'm sorry, PSPP also has a couple of other formats which it can accept from some certain other software applications, just like text, numeric spreadsheets, or open document spreadsheet files, which we are, I think OpenOffice Calc actually open document spreadsheet file. So that way I think you need not convert the open ODT or open document spreadsheet file into CSV or text file, doesn't matter. But anyway, so here I had written some code in syntax, so I'll just execute this, and to create or simulate the data set. If you observe, the dependent variable has only two responses, just like 1, 2, 2, 1, 1, 1, 2, so something like this. So 1 stand for, of course, maybe yes, or 2 stand for no, or 1 stand for I would like to develop a small scenario around this data. Just imagine that we collected this data from how many data points we have? We have 30 data points. So we just have to imagine that we collected this data from 30 patients, and the data deals with the attitude of the patient towards the healthcare spending or expenditure. So the X stands for the amount of money spent by the patient, and Y stands for the attitude. 1 stands for favorable or maybe unfavorable, and 2 stand for favorable. Why? Because SPSS convert these values into 0, 1. So where it makes meaning if I can convert, if I assign favorable to 1 and unfavorable to 2, and go to the variable view. There you can just assign the values where 1 stands for unfavorable and 2 stands for favorable, so that we have some meaningful context for the data, and I just leave X as it is. So you can just imagine as, or I can make rather the data a bit more meaningful by multiplying the data with some certain integer. Here multiply with 100. Let me again, I think now the data must be, the format of the data must be different. Yes, correct. So here let us imagine that the candidate number 1, I mean the case number 1, had spent some maybe 12,450 bucks on I mean towards his healthcare in the hospital, and whose response, I mean attitude, is unfavorable. And a person who spent 73,790 bucks, or in India we call rupees, is the response of that patient is favorable. Now there is another guy that he has spent 51,420 rupees, and he is whose response is favorable. I'm sorry, 2 stands for favorable, 1 stands for unfavorable. Now that way we have a convenient scenario to perform this binary logistic regression. Now let's go to the regression. Let me choose the binary logistic regression, where our intention is to predict the response of the individual for a particular value of expenditure. So now let me take the dependent value is the attitude, and independent value is the response. Let me choose this confidence interval 95%, and rest of the options you just keep default values and just press OK. Now let us go to the output window, and in output window you should be having the results here. And the very first table is going to be, this is the code for the binomial logistic regression. I think it's better to convert this into I will export that into an ODT file, so that it is easy for us to go to the documents and binary logistic regression. Now let me go to the documents, and I should be able to find this binary logistic, so that it is easy for me to just look at. I'll delete all unwanted so this from here. This is actually the code that we need to use in the syntax in order to perform this binary logistic regression. In case if you basically belongs to open source community who are most of the time interested in character user interface instead of a GUI, like graphic user interface. The very first table is going to be the dependent variable encoding. As I said somewhere in the beginning of the talk, PSPP will convert though we gave 1, 2, but PSPP internally will consider its own coding. Here the PSPP has assigned 0 to 1 and 1 to 2. So internally the code assigned to unfavorable response is 0 and favorable response is 1. And now this is the case processing summary. All 30 cases were used. We don't have any missing cases in this case, so there is no problem with this missing data. The next one is a model summary. This is the more interesting part of the analysis. Here we have -2 log likelihood, and this is the parameter or estimate that we obtain towards the whether our model is good or not. Actually, if we look at this, this table clearly shows that our model is not good because the R-square value is 0.01. That shows that only 1% of the variance in Y is explained by X, and I'm sure that we may not be able to make use of this fit in order to predict the response, in which case we may not be able to predict the attitude of the patients just by merely depending on the healthcare expenditure. So that is what is the result. But this is only a simulated data, so we need not comply in the data that this data is not able to describe the model or not able to describe the relationship between Y comma X. But in natural setups, or if the data is collected from the real world activity, then the values of this R-square may be different, where the R-square value must be close to 1. For instance, if a value of 0.9 simply means that 90% of the variance in Y is explained by X, whereby we can conclude that this model is pretty much useful for prediction. Now let's go to the classification table. This is also called as confusion matrix. Right now, if you look at this data, percentage of correct responses, that 100% of the responses that belongs to the category favorable have to be correct, and there are in fact only 0% of the responses that are correct belongs to the which in fact belongs to the category favorable. But anyway, that let us not, this is not our the part of interest. We are not interested in this particular table. Perhaps we may take up the discussion after some time in some other point of time. And this is what is very important for us right now, to talk about the prediction through binary logistic regression. Now the very first column, that is B, it is actually the beta. We have 0. Actually that is a bit difficult. A value of 0, whether so that unusual. So a value of that size is rather unusual in any practical setups. But whereas let us pick up the p-value. So the p-value is going to be 0.59. It very clearly shows that the beta value is 0, which in fact is true from the analysis. So our assumption that in other words, I can say that there is there is no evidence in support of the study hypothesis. The hypothesis is going to be that y depends on x. So here we are bringing an assumption that the patient attitude can be predicted with the help of healthcare expenditure, but whereas that is not the case. After going through the values in the table, our assumption rejected, and there is a lot of evidence in support of the or in other words I can say that the null hypothesis is accepted, and there is very less evidence in the data in support of the alternative hypothesis. Now this is what is very important for right now for our prediction. Here exponential e to the power of beta is 1, and with their respective lower and upper confidence intervals. And anyway, we are not interested in the constant. That is not useful for us to, I mean that is useful, but whereas we are not going to, as far as the hypothesis is concerned, we are not worried whether the constant is 0 or not. So anyway, finally we can describe a model like this. So we can simply go to the let's say the probability of predicting a particular response. Let's say for example in this case I will just make let's say, what about a person who is spending 10,000 rupees? How likely that we will so I'll rather put it, if x happen to be 10,000 rupees, then what is the probability of y getting either 0, 0 or 1, or 1 or 2? So this is what the question will be. Now that the probability of getting y to some value 1, 2 given x is equal to 10 is going to be 1 divided by 1 plus e to the power of minus, what is the beta 1? Beta 1 is 0, right? So 0 multiplied by 10 minus the constant, that is 0.60. So that is going to be 1 divided by 1 plus e to the power of 0.60. Oh, that's really an interesting expression. So the probability is just governed by the constant, but not by the coefficient. In this case the constant is beta naught and the coefficient is beta 1. So now let us go to our Calc back. Here I will try to find it out. 1 divided by 1 plus e to the power of 0.6. That's going to be the value 0.3543. 0.3543 is what is the probability p-value that that going to be 0.354354. So now the question is going to be, how likely, what is the probability that a person can move from unfavorable to favorable, 1 to 2, if given his expenditure is 10,000 rupees, that is going to be 35%. So that's pretty low. Okay, so in this way we can simply bring up some certain random values, and we can substitute those values in this expression and figure out our probability values. So in this case, so it is not that likely that we can see a patient changing himself from unfavorable position to the favorable position given his income is 10,000 rupees. So we can change this 10 into 20, 30, 40, 50, 60, and later we can see the p-value that way. Anyway, in all circumstances, whatever the value that we are going to substitute here, that is going to be 0 and the probability remains constant. So in all circumstances, we can come to some certain conclusion that the effect of expenditure on the favorability or unfavorability of the patient happen to be 0. So it is not possible for us to observe or study the patient attitude by merely depending on the healthcare expenditure. So this is going to be the conclusion for this particular scenario of healthcare analytics, especially belongs to the non-clinical area. Okay, so this is how we can perform the binary logistic regression in PSPP installed in Ubuntu 16.04. So stay tuned, and if you like my video, press like and subscribe to my channel, and stay tuned for the further content through my academy. Thank you. Thanks a lot.